Thank you, and thanks for the opportunity to be here today to talk on behalf of the team. Unfortunately, Brian McCormack is a project leader. He's not here today, so I'm presenting on behalf of the team on our work and on the use of UAVs for biosecurity. So let me just play a couple of videos that illustrate some of the missions and the types of environments in which we operate for the environment and also in agricultural crops. And the use of the technology on the drones, as you can see there, where you can put different types of sensors, multispectral, hyperspectral, LiDAR, different technologies that nowadays can be implemented on the drones and for surveillance of different type of activities on other types of in different environments. So, this project aims at evaluating the use of UAVs to detect and monitor high priority in-field biosecurity threats. We found that the technology is applicable across different scales, and we can monitor or could be used for different types of host and diverse environments. Specifically, the project, we concentrated on sugarcane, cereal aphids, yellow stripe rust, mildew rust, and gray phylloxera. So, drones come in different sizes and shapes. The small drones, you can buy them from Amazon, you can buy them at different places, and they have high-end products as well. Cameras also come in different types. RGB, multispectral, hyperspectral, but together with the drones comes the processing and the data, the planning of the mission, and the data analytics, and the health of the drone itself. So when we started the project 4 years ago, the technology was advancing, but it was still quite expensive to buy a drone. Nowadays, if we look 4 years after, you can buy a drone for $1,200, and it's got really good capability, high-resolution cameras. They're still limited in what they can do, but we're getting there in reduction of the sensors, the cost of the sensors, and what they can do. In the future, as we see the future, there's going to be a bit more, and you probably heard a lot of artificial intelligence or in the news and different algorithms that have been used to detect object recognition for in autonomous cars and systems like that. That is migrating to the agricultural sector and to other sectors. So, and you'll see some of that today. But what is needed is the technology adoption, much more user cases and more farmers and people using the technology, because that's driving the technology further and further. Not only for, so as the technology is driven by other sectors, it translates into the agriculture and the other way around. But there's a limitations where they can be deployed. We acknowledge that we cannot deploy them everywhere. There's a limit on what you can do. So we look at the biotic and abiotic stressors to prioritize where you can sample. There's also another limitation of where you can deploy the drones, depending on where you are. You have to comply with the Civil Aviation Safety Authority regulations to where you can deploy them. So you need to be aware of that. So once we prioritize an area, we can then zoom in and fly in those areas with high resolution, and the picture there illustrates that concept. To go to an area, identifying the area where you want to survey, and plan a mission and collect the data. Then in here we ask a question such as identifying and collecting plants. So the signatures that you can collect with hyperspectral and multispectral cameras mounted on the drones, the different environmental conditions that you can encounter, and the optimal flight distance that you fly at. And also the feasibility of using robotic elements or widgets to collect samples and specimens, and you will see some examples today. But how do you put all that information over the last 3 years together? And what we've done is that we created a knowledge tree about the use of drone technology and UAV technology for the purpose of biosecurity. And the idea is to maximize the return of investments. So yeah, the farmer, the agronomist buys the drone. What is the cost-benefit analysis of doing that? And for that, we've created this knowledge tree and a website that compiles this information. So where and when should UAVs be deployed? So for this, and Hamilton and his colleagues at QUT, by the way, I should say that this is a multinational project, so there's activity that happen in Kansas, some activity that happen in Victoria, and some activity that happen in Queensland. So I'm trying to put together those activities, and there's some reference publications that relate to more details about this. But Hamilton, in this case, and his colleagues explore with a Bayesian nets approach, the different scenarios of where UAVs could be useful. So what they found is that when the disease impacts are already effectively managed, and using an available option, the benefit of UAVs are not so high. But when for early detection, the UAVs were more provided an additional benefit, and in less monitored areas or disease systems, the use of UAVs did provide more accurate information. So in the Bayesian approach, you see it on the diagram, there's different parameters that they explore, and the details are on that publication. Unfortunately, it's not my area of expertise, so if you have any questions, please ask Hamilton or Frozen on that. John and his colleagues in Victoria explored the use of flying a drone, a fixed-wing drone, and a multi-rotor drone at different heights with different sensors. And they found that the drone flying at higher altitude, a fixed wing with an NDVI camera, wasn't as good as picking up a simulated disease in the vineyard. Whereas the multi-rotor UAV with high resolution image was able to pick up that the infected leaves, but wasn't able to pick up how many leaves were infested. Then John Weiss and his colleagues as well, with crop-safe agronomists, were able to do an expert elicitation, and what they found was that if you have airborne imagery, if you have imagery from a drone, the estimate of detection increases significantly from 0.4 to 0.78. And important as well is also optimizes the search effort. In Kansas, Brian and his colleagues studied the landscape effects of Hessian fly distribution in commercial wheat crops. The studies show previously unknown distribution of Hessian fly infestation within commercial fields, and the idea with that is to understand the landscape parameters so that you can then target the UAVs to fly in those areas. So again, the reports and details of that publication are listed in there. And in this area, remember that this area is about where you fly the UAVs. So how effective are UAVs at identifying areas of interest was another question. And in Kansas, Brian and the colleagues, they had the case study was an aphid numbers on sorghum plants that increased over time. And they used multi-rotor and fixed-wing UAVs, and what they found was that the multi-rotor UAVs provided that higher level of detail over the season. So with the fixed-wing UAVs flying higher, were not able to pick up the differences in DVI. The multi-rotor UAV was able to pick up those differences. In Australia, in collaboration with Jeff Pegg, we conducted experiments in marsh rust. And we have, what you see there is the camera, hyperspectral camera. We flew over exclusion zone that Jeff and his colleagues monitor regularly. And we were able to train the methods with our supervised classification to detect the effects of marsh rust in the forest. Again, I won't have time to discuss in full details this trial, but the results were published as well. And I think we're interested in how the technology in this particular case can be used. We're talking to Grant Smith as well about the use of that in New Zealand as well, and in other parts. We also use the technology in detection of phylloxera, but I'm going to save that for the fast science coming up. So I'll give you more details on that. But we found really interesting results of how to see the disease before you see it, if that makes sense. The hyperspectral camera is capable of giving us an indication of where the disease may be before you physically see the damage. because of the hyperspectral signature. The next question was if UAVs can be used to identify and collect plant pests. So there's some developments done in Kansas and in Australia on prototype widgets. So in this case, it's a suction trap that sucks the insects, or some developments at the bottom showing with the robotic arm on a drone to collect some samples. So, next. Another aspect is, okay, so far we've been talking about above the canopy, above the tree canopy, but what happens if the disease is sub-canopy? And Brian and his colleagues in the US, they have this UAV with a boom, and it's got a camera underneath. And you see the level of detail there in the picture with the square. See if I can point it over here. So here, the level of detail, and then zoom in into that insect and to that. So the idea is that information such as this from the drone, this image can be uploaded, for instance, to Pest Point as well, so that you can, an expert can diagnose or give an indication of what's in the field in those cases. So the drones can provide that level of, can help us on that higher level identification, but also can assist in the sub-canopy identification as well. So how do we put all of this together? How do we combine all of, and it was a really rapid overview of the different case studies that we did in Victoria and in Kansas and in Queensland about the use of UAVs. And we learned a lot in this journey over the last 3 years on what works, what doesn't work, what are the optimal technologies, what are the optimal heights at which you fly the UAVs, what sort of sensor to buy, what sort of UAV to buy. And we put all of this together. We thought the best way to do it was through a knowledge tree. So there's an engine inside this website that takes you through a journey of questions. And so we created a website so that users can interact, and it asks questions and prompts questions to the users and digs further and further into helping them in, if you were to use the technology, what would be the steps to take? So it's organized in different branches, and these here are the different branches. So one of them is regulatory concerns. So what are the regulations in Australia? What are the regulations in the US? It can be expanded to other countries as well. What is your research problem and question? What is the knowledge of the technology? What is your knowledge of pest risk and management? And the content is subdivided and divided in questions and statements. So in this tab, in this part of the tree, it makes users aware of the literature or pest plan interactions that will direct them to decisions that are more effective for surveillance. In this other aspect, it brings broader understanding of the technology, assisting the user or the person that is visiting the website on the technology itself. In this other part is the management. It raises awareness of modeling techniques and aspects of sampling techniques that could be used as well. In this other aspect is the different technologies, different types of UAVs, different types of platforms that can be used. And it guides them through the reports and the different things that we did during the project. So in conclusion, the research is a significant contribution. We believe it's a significant contribution to the understanding of the utility of aircraft, drones, and sensor technology for pest surveillance. There was limited work when we started 4 years ago. It's really great to see that the work continues to expand, not only from us, but others in the community. We conducted many workshops and seminars, and it's really good to see the uptake of the technology, that they're not just a toy, it's happening. Benefits, more targeted approaches, reduction in sampling time, improved efficiency of sampling, effective use of resources, avoided loss of production. So what do you buy or if you were to buy a UAV or you were to work in this technology? So the idea is that to have UAVs or drones that have a multifunctional, that you can plug and connect different types of sensors onto them. So with that, I'll thank you. I thank the Plan Biosecurity on behalf of Brian for the project, and all the collaborators and all the engagements that we had through the project. So thank you.